Hey friends, welcome to our first installment of a field guide to particle physics. Today we're going to be talking about something that's hopefully familiar to everybody, helium gas. Helium will give us context and preparation for hunting down the more elusive particles out there. The story of helium and why it's so often in short supply is a layered and textured story in its own right, definitely worth telling. It brings together ideas from chemistry, technology, medicine, shipbuilding, rocket engineering, geophysics, and quantum mechanics. Some of the questions that you'll be able to answer after today's video include, why is helium so hard to find in the wild? And what makes helium unique amongst other gases? What does quantum mechanics have to do with the production of helium? And what is the relationship between helium and radioactivity? Also, which is really amazing to me, what exactly is the relationship between plate tectonics, the aurora, and helium? And remember, if you have any other questions, please reach out and start the discussion. But before we get to all that, I have a question for you. Do you remember your first experience with helium? I think I do. When I was a kid, I remember being seriously confused by balloons. On TV, at the grocery store, at parties, they were all floating. They had to be tied down with ribbons. And yet, all the balloons that we had at home were just kind of flat. The answer came one day in a pavilion near my elementary school. I saw somebody filling balloons, and not from their lungs, but from some kind of giant metal canister. And all those balloons were floating. "What's that?" I asked whoever was around me. "Helium," somebody said, "for balloons." Helium, I said to myself, helium. Just to get us on the same page, let's review some basic facts about helium. Helium is the element with atomic number 2, which means that its nucleus has 2 protons. And because of that, the helium atom has 2 electrons in orbit around them. As it turns out, the helium nucleus also has neutrons. Neutrons are particles that are like protons, but without any electric charge. Helium comes naturally in 2 stable variants, helium-3 and helium-4, with 1 and 2 neutrons, respectively. Other isotopes of helium have been created in the lab, adding 3, 4, 5, 6, 7 neutrons to the helium nucleus. But most of those just decay almost right away. Helium-6 and 8 do hang out for the greater part of a second, though. Virtually all of the helium found on Earth is helium-4. There's very little helium-3. And because they're stable isotopes, that suggests that there is a different mechanism for their creation. And indeed, helium-3 is primarily created in nuclear reactions in stars. And helium-4 is created, well, that's the subject of this whole video. Now, because chemistry depends almost entirely on electrons, the chemical properties of helium-3 and helium-4 are the same. Helium is a gas at room temperature and pressure, and it's a gas with really low density. The air that you and I breathe is 10 times more dense than helium, which accounts for that inhale helium from a balloon and sound like a chipmunk party trick. But as we'll see, being a gas with really low density comes with a host of other problems. Heavy things sink and light things rise. This is true in both water and air. Just ask any swimmer. Air bubbles always rise to the surface of the water. The same is also true for gases. When we talk about gases, we don't really talk about weights, we talk about densities. Our atmosphere is comprised almost entirely of nitrogen, oxygen, and argon. As you can see, they all have a similar density. This is no accident. Hydrogen and helium gases are considerably less dense, and as a result, they tend to float or rise in the atmosphere. Anyone who's held a helium-filled balloon can attest to this. And therein lies the trouble for helium. If helium is constantly floating away, where do you go to find it? Shouldn't all of it just float away into space? Well, yeah, of course it does. That's why there's a shortage. We haven't always used helium in our balloons and our blimps. We used to use hydrogen. Hydrogen gas works the same way that helium does. Both hydrogen gas and helium are lightweight with respect to our atmosphere and so tend to be buoyant and rise. But hydrogen is far more abundant on Earth than helium is. And this is because hydrogen forms chemical bonds with ease. Indeed, almost every organic molecule there is comprised primarily of carbon and hydrogen. Hydrogen also bonds with oxygen to form water, which fills our oceans. Bound up in these molecules, hydrogen just can't float away. But helium doesn't form chemical bonds. It doesn't react with other elements. It remains a gas and therefore tends to float away. But you see, hydrogen's propensity to interact with other molecules tends to be a problem. It's combustible, especially in the presence of oxygen. Why helium is immune from this phenomena, where hydrogen is not, is a question for chemistry. And at the present moment, it's a question worth asking. From a physicist's point of view, chemistry is just the study of electrons. You see, in physics, we love to study things from first principles. I can tell you all kinds of things about how electrons buzz around the nucleus of a hydrogen atom. But even bringing two atoms together makes for a really complicated problem that is difficult to solve with physics. Through experimentation, chemists have formulated some empirical rules and exceptions for how atoms come together to form molecules. The version you're probably familiar with is the valence theory of molecular bonds. And the very short version has two big ideas. First, an atom will seek out as many electrons as it takes to become electrically neutral. That's the dominant effect, and that's just electricity. Second, those electrons prefer to gather together in clumps of a particular size. They prefer this so much, actually, that two electrically neutral atoms will actually come together to share electrons so those electrons can form those clumps. Clumps of like 2 or 6 electrons. Actually, it's a little bit more precise than that. The clumps go in a particular order. 2, 2, 6, 2, 6, 10, 2, 6, etc. This is a secondary effect. It's a much weaker effect, but it's an effect driven by quantum mechanics. Before we continue, there are two insights from quantum mechanics that I want to share with you. The first is, anything that can happen will happen, given enough time. And the second is, particles are always seeking out the lowest possible energy. As it turns out, bringing atoms together so their electrons can form these clumps actually lowers the energy of both atoms. This is all very abstract, so let's go ahead and see some examples. Hydrogen gas, HH. Alone, they both have 1 electron. Together, they have 2. These 2 electrons can form a clump, so they do. The energy that 2 hydrogen atoms can save by coming together and forming a bond, it's about 4.5 electron volts. Not bad. Let's do nitrogen. Nitrogen gas, N2. Nitrogen has 7 electrons. So that's 2, 2, and 3. So a pair of nitrogen molecules can each share 3 electrons to get to that clump of 6. Okay, great. Let's try methane, Ch4. Carbon has 6 electrons. That's 2, 2, 2. So it would like to share 4 electrons to get to a clump of 6. Do you see the pattern there? Each hydrogen wants to share 1 electron to get to a clump of 2. Water, H2O. Oxygen has 8 electrons, forming clumps of 2, 2, and 4. So it wants to share 2 electrons to get to 2, 2, and 6. So it pairs up with 2 hydrogen atoms. Okay, great. This hopefully is intuitive by now. You should try CO2 for yourself and see what you get. Now, if you want to see these rules get cranky and super complicated, try to do this for oxygen gas, O2. It will quickly show you that these are empirical rules. This isn't a fundamental theory. It's just a model for how to explain the world, but it's a pretty effective model. Chemists, of course, know how to solve the complicated equations of quantum mechanics, but this generic Lewis structure model is pretty informative still. Let's look at helium. Helium has 2 electrons. What about neon? Neon has 10 electrons. Those form clumps of 2, 2, and 6. Huh. What about argon? Argon has 18 electrons. 2, 2, 6, 2, and 6. What do these 3 elements, helium, neon, and argon, all have in common? They're inert gases. They don't form bonds. And they don't need to. Their electrons already form clumps on their own. So, in summary, helium doesn't form chemical bonds because its electrons are already stabilized. They're already in their lowest energy state. But what's so perplexing about helium is that the nucleus has as well. Part of what makes chemistry so hard to understand is the sheer diversity of elements. With well over 100 different flavors, the number of molecules that can be made is effectively limitless. Nuclear physics, by contrast, feels a little bit more manageable. The nuclei of atoms are considerably easier to get your mind wrapped around. They are super tiny globs made entirely of protons and neutrons. And that's it. Now, protons and neutrons themselves are extremely complicated. They are sloppy bags of subatomic particles that are extremely difficult to describe mathematically. But because all of that madness is confined within these tiny packages, we won't worry too much about them here. Except to say that all of that crazy physics leaves a residual stickiness on the edges of these particles. That stickiness is still pretty powerful. Pulling apart a hydrogen molecule costs about 4.5 electron volts of energy. Pulling a proton off a helium atom, that'll cost you almost 2 million times as much energy. It's a different kind of physics. Now, here's a plot of what the energy cost looks like across all different kinds of nuclei. Going left to right, we're looking at a nucleus of 2 particles, all the way out to a nucleus of 238 particles. Each dot corresponds to a different nucleus of a different kind of atom. You can think of this as a plot of how tightly those nuclei are bound together. As you can see, as the nuclei get bigger, they get more and more tightly bound. Eventually, that plot hits a maximum. That happens around iron 56, which is one of the most tightly bound nuclei there are. After iron, the nuclei start to get a little too big. Slightly easier to break apart. A little less stable. Remember, quantum mechanics always sniffs out the lowest energy possible. Another way to interpret this is that smaller nuclei would prefer to fuse together, and the bigger nuclei would prefer to break apart. Of course, just because the nuclei want to fuse or break apart doesn't mean that they actually can. Pushing 2 hydrogen atoms together to form helium is still really, really hard. Their positively charged nuclei are very repellent. So hard, actually, that it takes the gravitational bulk and heat of the inside of a star to get that reaction to go. Here on Earth, it would typically cost far more energy than would be saved by the nuclear fusion. Now, for atoms, the count of protons in the nucleus effectively determine its charge, and therefore its chemistry. The count of neutrons helps to determine its mass. And for our purposes here, that's basically it. Any nuances to nuclei involve their stability or their tendency to break apart. When they do break apart, we call that radioactive decay. It's a secondary effect, and it's the result of quantum mechanics. To get a feel for some of that nuance, let's take another look at the binding energy of helium-4. Compared to similar nuclei, it's a serious outlier. It's very tightly bound. There's something really curious about helium-4. Believe it or not, I just shoveled this yesterday. We woke up this morning to bursts of electrical energy outside and flickering power. So I didn't get the full amount of time to export the whole video. So this is part 1. Boy, am I excited for part 2.